electrons into a target and it creates radiation. Well, the electron, because it's a subatomic particle that is not divisible yet, when it hits that, it gives off gammas. But if you have something that can break apart, it'll hit, and maybe you have two quarks that are tied together go this way, and one quark go this way. Different charges go in different directions, and they have those spins to where you're talking about what happened, how that happened. Well, there's a huge mathematical model that takes those and figures out what the mass is. And if you know the masses of those, and you know how you took the picture, and you know how long your picture was open and what happened within that, you knew the speeds of them. If you know the mass and the velocity, you know the momentum. The momentum is always conserved, so we know if we hit it with this particle, we know its momentum. We know the momentum of that, so we know what the mass of that one is, because I know its velocity. And if I know the mass of that, that's different than anything we've ever had. Ding, ding, new thing we found. Right? You say, well, what does anybody care? Well, you don't realize how many things that we have today are based upon this type of research. There's kind of an idea that I have is that most things are anywhere from 4 to 10 times above your head, right? As an adult, right? And I told you mine. I have a bachelor in science, and then there's a master's, and then there's a PhD, and there's multiple PhDs. I'm at least 2 degrees below the people that are doing this stuff, right? At least 2. But most of this, when it comes to activating in real life, it's way up here. What they're doing is way up here, and the actual application is way down here. Right? When NASA first did its research about going into space, somebody said, you know, we're going to have a face shield on their helmets. But they're going to be in space, and the atmosphere won't be there. What's the effect? What do you think the effect is of the sun on people if they don't have the atmosphere taking away some of the intensity? And they went, huh. I guess if they look at the sun, their face will burn off. So we have to figure out a face shield. Well, if you have UV protected sunglasses, you're welcome. 1960s was when they were doing this, and we have sunglasses. Now, we don't think anything of it. We pick up a pair of sunglasses. You can spend anywhere from $5, or you go to Dollar Tree and get them for $1. I don't recommend those because they don't have UV protection, but about $5 you can get something with UV protection, or you can spend $250 on ones that are cool that you will break within 6 months or lose. Right, so that's, but I have Maui Jims, or I have Costas. Right?
I got Walmart.
My regular glasses are Costas, but they have real lenses in them because I'm blind as a bat. So I put my sunglasses on their prescription, right?
Okay.
Well, the idea of the coating came from NASA from many years ago, and so that's a benefit to us. Sunscreen is actually a benefit to us from that. So there's a lot of things that are way above. And eventually they trickle down into everyday life because somebody figures out that that can be applied to some sort of product. Okay? So as we're going through this idea in those high energy things, people are like, why are we wasting our money? And I says, well, if we just start saying, well, give me that product and give me that product and give me that product, these are all from those high energy experiments, just give me all, what? No, you can't. I mean, for goodness sakes, we know how electrons work, right? So we built one of these. And everybody says, can't live without one of these. Well, yes, you can. Trust me, you can. I grew up without them, so you can live. Well, just not as well. Whatever, all right? But because we did experiments with electrons, and we did stuff with solid-state materials and PN junctions and integrated circuits, we now have access to some of this stuff. But it's taken years. You're just the beneficiary of everybody working hard before you. Now, your job is to go out and be the next person to do that in business or in engineering, technology, or in literature. I mean, how many really classic books have been written in the last 50 years? I mean, classic books. Ones that will last like the old books have. I don't know. That'd be an interesting thought. Maybe that's a thesis point for next year. Where have all the classics gone?
Is that
They're replaced by Facebook moms in the all day.
Well, here's the thing. When somebody read The Lord of the Rings the first time, they knew. They knew.
What about Harry Potter?
Could be.
Yeah.
I could be. I've never read them. I don't care about them
They're so good.
at all.
I've never read
Right? I don't want to waste my time with that. Right? That's just personal. But they very well may be a classic. So that'd be kind of an interesting thought process, don't you think? An interesting thesis topic. You do the same thing with music, right? Same thing with art. What are the classic pieces of art that are being done today that will be last forever, like Rembrandt, like Monet, like Degas? And if you don't know who they are, then you probably ought not do the one on art, right? All right, so what we have in this atom is we have these protons, electrons. Now, did you notice that the proton has a +1 charge, the neutron 0 charge, and the electron has a -1 charge. So for every proton, there is an electron in a neutral atom. Right? So look at your periodic table, and let's take a look at carbon. Carbon is kind of the model for a lot of stuff that we do. All right? So carbon, I'm going to show you how I write carbon on the board. Carbon is 12,6. Now, that 12 is called the mass number. All right? The mass number is 12, not the atomic mass. Can anybody tell me what the atomic mass is, Sadler?
12.0107.
12.0107.
So it's just,
That's the atomic mass.
it's round.
Meaning that includes what?
Um,
What's the word we use?
ticket numbers.
Isotopes. It includes all the isotopes, which we're going to talk about today, right? So carbon, that's the atomic or the mass number. This is the atomic number. Okay? Now the atomic number gives us two pieces of information. I think I've told you this before, but we now have to remember it. All right? It's the number of protons and also the number of electrons. Now I'll put a P with a plus next to it, showing that it has a positive charge, +1. The electron has a -1, so it says the number of protons and number of electrons. Okay? So, then how do I get the number of neutrons? Remember what we said? Simon?
You take the atomic number and divide it in half.
You do that for the first 20. But after number 20, that didn't work. So where we have been, your estimate is correct. But when you get to uranium, which has 238 and only has 92, it's not. The number of neutrons, here's what you do. And the reason that I put it this way is it makes it easy to subtract. So I take 12 minus 6 is 6, and that's how many neutrons I have. So you could take any element and do that with it. Okay? So Miss Miller, do you have your periodic table out? Would you get an element and tell me the name of it? Boron. Right. Boron, if I'm not mistaken, has an atomic number of 5, and I think it has an atomic mass of 9?
10.8.
10.8. So it's 10.8, so my mass number would be 11.
Because you round.
All right? Always round for the mass number, not the atomic mass. We'll use the atomic mass later on when we're talking about isotopes, right? That's how we're going to get the atomic mass. So from looking at boron, how many protons? How many protons? 5. That number. How many electrons? 5. How many neutrons? 6. So the math is not really that hard. right, to do this type of idea. Okay? Now, talking about that. So that's on your periodic table. It should be pretty straightforward, right? And so what you end up having with Rutherford's model, let's take a look at Rutherford's model. And let's just take a look at hydrogen because it's the simplest one to do. How many protons does hydrogen have?
2.
Protons. 1. It's the first one on the list. Left side, top, right? So it has 1 proton. So I'm going to make a little dot for my proton. How many electrons does it have then? 1. So it's going to fly around like this. I'm going to put an electron out here, and this is a proton. Now you notice, protons and electrons, they add up to 0. Most atoms in nature are charged 0. If you had an atom of it, it'd be charged 0, which means it has the same number of electrons as protons. Okay, now, what do we know about opposite charges? What do they want to do? Attract. Why don't they attract? Why don't the electrons slam into the proton?
The neutron.
Nope, there's no neutron in that one. Nope.
Is it because the electron is constantly moving?
Okay? It's moving in a circle, right? And I don't know if this really exists in this drawer, but I'm going to pull it out and go, yay! Of course it does. Okay, this is my electron. Okay? My electron, my proton. Now, without motion, this is going to attract like this. But if I keep it like this, it's wanting to leave. If I let go of this string, it's going to fly away, right?
Yes.
Which means it wants to go away the whole time, but what's happening is my hand is pulling it into the middle.
Oh.
And when my hand is pulling it into the middle, that's a force pulling it in. It wants to go out, so it's called an orbit.
Centrifugal force.
Stay away from the word centrifugal force. This is actually centripetal acceleration. And we'll talk about centrifugal force next year as to where and when it'll apply. Okay? All right? So this is actually a force called centripetal force, pulling in on this to keep it in orbit. The same thing happens with an electron flying around. Right? That electron's flying around. If it ever slows down, it'll spiral in and slam into the nucleus. Which it never does.
Because it can't.
Ever! Because then all these atoms would annihilate. And they wouldn't be the atoms that they are today.
But we could slow it.
Well, we can slow it down, but it doesn't do it naturally. Right? Yes, sir.
Just like the same concept as the moon, like get that mass of the Earth.
Moon in the orbit of the Earth. If the moon stops moving, it will fall into the Earth. To give you an idea, that question right there that Judah brought up is this. Isaac Newton is sitting there under an apple tree. Remember he got hit on the head with the apple? He didn't get hit on the head with the apple. That's just a thing for children, right? It's not the reality. Sitting under an apple tree and he's looking, he sees an apple fall and goes, the apple falls because of gravity. Why doesn't the moon fall? Because he figured out it's in orbit, right? And then he came up with something called the universal law of gravitation. And all of a sudden, we can now explain the motion of heavenly bodies, right? So you got stars, you got moons, you have planets, you have whatever. We can explain all of that, predict where it's going to go, and why, and therefore know the mass of an object. Why? Because if I know the mass of this one, I know what the orbital speed is, I know how far it is away, I can predict the mass of this object. Really? Yeah. All those numbers you find in books that people have figured out, it's science. It's because people were curious. Well, the curiosity here is that these have to be in orbit. They're not just hanging out. See, this is the problem with the plum pudding model. Positive and negative annihilate each other. Create a zero charge. Plum pudding model didn't do that. Rutherford's does. Okay? Yes, sir.
So I have a question. If we were to, say, stop this process and the electron was able to hit the proton, would that be a radioactive?
This would be bad. All the protons would become neutrons and all the elements would disappear.
Something magic.
Wait,
And
so
the reason we know that is we can take a we can take a neutron, blow it apart, and get a proton and electron, which is how carbon-14 works. Okay? Yes, sir. Last question before going.
So if we just did it with one, it would just disappear.
They become a neutron.
Oh.
Under normal circumstances, those would become a neutron. Neutron isn't an element. So hydrogen would cease to exist, you'd have a neutron.
But wouldn't it be like a special
Nope.
neutron?
Be just a neutron. Because like I said, I can take a neutron and blow it apart and create a proton and an electron. It happens every day in the atmosphere, and carbon-14 is the result.
I thought they were made of quarks.
Yeah, they are, but I can blow this apart and get a proton and a neutron.
That's
or
how we
proton
know
electron.
that's
Trust
how we
me.
know that neutrons have
Yeah.
both those.
There's something called an atomic electron, which create neutrons. Neutrons are actually a combination of protons and electrons. A neutron, neutral, right? Yeah, trust me. It's crazy. That's why the people are so high above where we are, because they were the ones who thought about this the first time. They're not being confused by an explanation of it. They're thinking of it. Now, let's take a look at another. Let's take a look back at boron here. Boron says, according to the Rutherford model, that there's 1, 2, 3, 4, 5 things in the nucleus, and you have 1, 2, 3, 4, trying to draw it correctly, 5 things flying around. 5 electrons flying around, right? Now, the next problem comes in is how in the world do those protons live in the nucleus right next to each other? Because don't like things repel? And yet we're going to take all these protons and we're going to go, and they're going to stay together. Yes, sir?
Wouldn't the orbits draw them together because all the orbits are in different directions?
Nope. Actually pull them apart because they are pulled out to the negative. The orbit's actually trying to break the nucleus apart by pulling them toward the negatives. What causes that? Well, let me tell you. We don't know. Isn't it a wonderful thing to say we have no idea? Now, we do know how much force required to pull that together. For example, if you take a north and north magnet and you go like this and you push them together, you have to push them together because there's a force pushing them apart because they're exactly the same, north and north. You're putting in, you're like, right?
It's like
So guess what they call this? Right? The strong force. It's an incredibly strong force. We do not know where it comes from. We do not know why it works. All we know is that it exists. Now, trust me, we're going to figure it out. And then there'll be something else that we don't understand. There's always something we don't understand. We're never going to get to the end of this. Not before the Lord comes back. He is far more infinite than we can imagine, so there's all kinds of things that we manage it. We go, okay, well, that because I begin to understand a little bit of that. But something called a strong force holds the nucleus together. Okay? So boron has 5 in there, so that force is a certain amount. Uranium has 92 protons. That's going to have more force. The neutrons that live in there do not affect the force, right? Neutrons are just kind of packed in there, kind of like this, if you can imagine. All right, I'm an old man, I walk, and I look at the scale. I'm supposed to step on the scale at the doctor's office. So what's the first thing you think I want to do? Take off my shoes. Why? I weigh too much. That's not really my weight. That's my weight plus my shoes and my phone and my keys. So you're like wanting to pull stuff out and says, no. Every time you come in, you're dressed like this. I just want to see if your weight is changing. I'm not worried about your total weight. I'm like, oh. So I step on the scale, right? And the last time it was this, and now it's this, and now it's this. And I'm losing a little weight to the medicines and everything that I'm taking, which is not a bad thing, right? So I'm able to watch the change, right? But you know what? When you really want to know how much you weigh, you pretty much take everything out of your pockets. You take your shoes off, making sure you weigh as light as possible. You step on the scale, hoping that it's the number you want, all right? Neutrons just add mass. It's like getting on a scale carrying a shot put. They just add mass. As far as we know right now, they just add mass. Now, one of the problems we have with that is that Sometimes if we have too many neutrons or not enough neutrons, it makes the nucleus unstable. And we have radioactive materials,
Yeah.
right? Carbon-14. Carbon-14 is made from nitrogen. Nitrogen is 14.7. High energy particle comes in, slams one of the electrons out of the orbit, slams it into the nucleus, and one of the protons in nitrogen actually flops to a neutron, and we get carbon. This is now radioactive. Every 5,730 years, the amount of it cuts in half. This is where we get carbon-14 dating, right? We talked about that. But this is an example of an isotope that is radioactive. Not all isotopes are radioactive. Some of them are stable. But if you have a new set of neutrons, so take a look at each of the things on your periodic table. You'll see a number of protons, which is the atomic number, and then take a look at the mass number. Just round it. That's how many neutrons. That's a stable isotope. Now, you get into some that are radioactive, like uranium. Uranium's radioactive. Technetium's radioactive. Thorium's radioactive. A lot of the heavy ones are radioactive because they have a whole lot more neutrons in the nucleus, which makes them more unstable. They want to split apart into other things. Okay? Now, on page 102 of your book, there is a chart. And I want to tell you on that chart what you need to know. You need to know column 1, electron, proton, neutron. Relative mass. Right? Relative mass. Protons 1, neutrons 1. They're the same mass, essentially. I want you to change the fraction for the electron. I just want you to put a single line through it. Not that it's wrong, but we're going to use 1 out of 2,000. I want you to remember the electric charge and the location. Those masses, you do not have to know. I will always give those to you. So the first 2 columns and the last 2 columns I want you to know, which you should. I mean, you look at that, you probably already know. Middle column, not so much. All right.